All right, AP Physics C. Just a little bit of an energy review here. This is gonna be in a couple parts here. Um, just kind of want to review kind of how we get the basic energy equations. Um, so you got to remember, energy isn't really a thing. It's a way to keep track of what's happening in a system. It allows us to solve problems that we normally wouldn't be able to solve. For instance, if you look at a roller coaster ramp type problem, right? Um, we want to figure out the speed at the bottom, right? Let's say it starts off at rest. Well, you might say, okay, V equals, if you didn't know anything about energy, right? You'd say, okay, V equals V initial plus acceleration times time. But I don't know time, so maybe I could use V squared, right? V squared equals V naught squared plus 2A delta X. Well, I suppose I could do this. I can't really do, straight line. I have to find the path length here. So maybe I would know how long the ramp is, right? But then how do you do the acceleration? Well, the trick here is the acceleration is the component of gravity that's parallel to the ramp. So that's actually changing the whole time, right? So in the middle we have a really high acceleration, but we'd have almost no acceleration here and here. So that doesn't really work either, right? I'd have to have a function based on the shape of this line of the acceleration, and I'd have to do some calculus to be able to do it. So those techniques aren't going to work. However, we do have a different way to keep track of the system, and that's energy. And really, energy comes from forces. Change in energy we call work, right? Which is force times distance, right? We would have said FD last year. Well, it turns out it's not exactly that simple, but we can, think about the force of gravity pulling it down a distance. There's no force parallel here, right? So we can just say, okay, it's the mg over the distance it falls, which we often call h. So that would be, well, we say delta h or delta y, I suppose, maybe. Delta y. So change in potential energy due to gravity is mg delta y as it falls down. Now, we usually don't include the delta, right? We usually say, what's the energy at a particular location. All right, so UG at a particular location is mg times the height at that particular location. The bottom at 0, the top it's mgh. So delta UG would be negative mgh as it fell, right? We can do the same thing for spring energy, but we do run into a problem with spring energy. Because work equals force times distance. All right, so delta US equals the spring force times however far it's stretched. But what you got to realize about this is it's not constant, all right? In fact, it's going to increase as x increases, all right? Because the function is actually fs equals, fs equals kx, actually negative kx, because, believe it or not, this is a vector quantity, and if the displacement of the spring is, if here's an object, right, and the spring's over here, and you displace it this way, the force of the spring is opposite the displacement vector. So it actually puts a negative sign there to make it, okay, if delta x is positive, then the force is negative. If delta x is negative, the force is positive. The problem here is this variable is changing, right? And you realize that, oh, this might involve some calculus, and it does, which we'll get to later on, or you can analyze the graph, an important thing here, right? For this graph, right, if I have force and position, I call it F and R to make it generic. Well, I'll say FG and y and fs and x, right? Fg and y is linear. Turns out the area under a force versus position. Area under F versus position is change in energy caused by that force. So look, the value of the force is mg. How far it's stretched is h. So that's the area under the curve. Spring potential energy, right, ends up being 1/2 base times height. So it actually ends up being 1/2 of the spring force times x. Or if you put it all together, you get delta US equals 1/2, and put in kx here, you get 1/2 kx squared. And it really is delta x squared. So there's our spring potential energy. So, usually typically, again, we kind of, we don't write it as change. We usually write just us at a particular point in our system is 1/2 kx squared. Now, gravitational energy, kinetic energy, it's a little bit different, right? Area under the curve doesn't really work for kinetic energy. You can look at the basic definition, though, of force of work here, right? This is more of an algebraic proof. It's kind of cool. So let's say there's some force pulling this, right? Starts V naught 0. V final is, we'll just call it V. Let's say it displaces it some distance, delta x. All right, so check this out. Work done on the box by that force, just a single force, is force times distance. Well, force is mass times acceleration. I should call that delta x, I suppose in this case. Now, I don't know anything about time. Time never shows up in our energy equations, right? So if we use the v squared equation, all right, solve for delta x. All right. A's cancel. You get 1/2 mv squared for the work done on the box by that force. And really this is the KEF. Remember, it's change in energy is work minus KE initial, which is 0, right? So KE equals 1/2 mv squared. We call it like that. So it's really just using work energy and kinematics, and you get that. And that is caused by a force. If it's the force of gravity, you can say, okay, the potential energy gets converted into kinetic energy. If it's a spring force, you can say the spring potential energy gets converted into kinetic energy. If it's just a random force, you just say that force times the distance equals change in energy. What's kind of cool here, if there's a whole bunch of forces acting on this, right? Turns out that the net change in kinetic energy would equal the net work done, which would equal F net times the overall displacement. All right. Now, I'm not being perfectly careful here. In this case, we see it would have to be the net force parallel to the displacement. All right, and it's something called a dot product, which we'll talk about later on when we have a little more time. So, just to kind of wrap things up, basic energy equations: PEG, MGH, which actually we're going to call UG, PE spring, 1/2 kx squared, but we're going to call that U sub s, KE, 1/2 mv squared, we're just going to call that capital K. That's the upper level way of writing this stuff. And the last one is the work done on an object is equal to the component of the net force that is parallel to the displacement vector. Alright, I guess I will talk about this a little bit right now. And we write it without the parallel. We put that dot in there. Alright, and that is a flag to say if you have some force, you have some displacement vector, say that's delta r, this is your force vector, that's the angle between the two vectors, you know, I can move this up there and see it. Alright, I need the component of F parallel to r, and if this is the angle between them, F parallel, the magnitude of F parallel is equal to the magnitude of F times the cos of theta. So often we'll see this work written as the magnitude of F net times the magnitude of delta r times the cos of the angle between them. Alright, and even though there's two vector quantities involved here, the answer is a scalar. It's just going to be a certain amount of work done by that force. Pretty cool. So that's the dot product. There is a way to do this with vector notation that I'll probably show in a separate video. So again, work is the component of the force parallel to the displacement multiplied. It's like almost like the projection, right? Here's F parallel. Right? It's the projection of that vector onto this vector multiplied by the second vector. That's a specific instruction called a dot product.